The next speaker is Sadeh from DESY, and he will be speaking on the graphical user interface of the Cherenkov telescope.
Hi everyone. I know you're probably anxious to get to delicious lunch, so I promise that after a few technical slides, there will be some fireworks in the end, so it's worthwhile for you to stay. So in case you're not familiar with it, CTA is the future observatory for very high energy gamma rays. It's going to come online starting from 2020. We're going to start deploying telescopes on the ground. We'll have imaging atmospheric Cherenkov telescopes that will be comprised of 2 arrays in the northern and southern hemisphere. Now, the general principle of how this will work is that you start with very high energy particles, photons or cosmic rays that come from outer space. They hit the atmosphere, and then they initiate particle showers. And part of these particle showers is generation of Cherenkov light. So this is this blue cone here. And then the Cherenkov light is sampled by a series of telescopes that are arranged on the ground. And what the telescopes actually see is depicted here. So here we have images from 2 different cameras. And what you can see is that, well, if you start from here, actually, this is, let's say, 1 camera. Then it sees the projection of this pool of light. And then when you combine images, in this case from 3 telescopes, then you see different views of the same shower from different positions on the ground. And then you can reconstruct some of the basic properties of the original particle that initiated the shower to begin with. And then you can use this to do awesome physics. Now, the main instruments that we will use are these imaging atmospheric Cherenkov telescopes. And for CTA, we're going to have 3 types of these telescopes: small, medium, and large size telescopes. And each kind is sensitive to a different range of energies. Now, the interesting aspect of this with regards to a user interface is that we're going to have a very large variety of hardware. So you can see here that we're going to have different types of small size telescopes, and then also even for different camera types, for instance, for the mid-size telescope. So that means that we're going to end up with a lot of variation on the type of hardware that the array would be composed of. And we want 1 or 2 operators in the control room to be able to figure out what's going on and to control the array, considering this complexity. Now, what saves the day, in a sense, is that a lot of the operation for CTA is going to be automated. And that means that what we want to have finally is that the operator comes in the beginning of the night, sees that everything is working okay, presses a button, and then operations start. And then we're going to have a prepared schedule that would execute the observations that we want to see. So, for instance, allocate 20 telescopes to look at this position in the sky, and the other telescopes to look somewhere else for 20 minutes, and then shift and do something else. So now when we design the operator interface, then on the one hand, we know that we want everything to be automatic, but on the other hand, we also want it to be usable and to encompass the wide range of problems that could come up in the middle of the night that the operator would have to address. So we took some inspiration from ALMA, and we're designing the user interface in a way that is very user-centric. So we're having dedicated workshops with experts from human-computer interfaces, from our colleagues from INRIA. It's an institute in France. And they are helping us to meet with other groups from CTA and with also future operators of the array, and to try to figure out exactly what the GUI of the operator should enable the user to do, and also how it should be designed considering this. And then these workshops have been very successful. We do mock-ups, we draw a lot of stuff on a whiteboard. No one is allowed to use a laptop, and we all really push through. And then in the end, we came up with a few panels, and we'll keep developing this with different groups of CTA from different aspects of the operations as we come along. So in the meantime, in parallel, we've been working on a prototype, and this has mainly been done by myself and a couple of other developers, with also a lot of assistance on the back end from COSI Lab, who've been very good collaborators for us. And then this prototype that I'm going to show you in a couple of minutes, it's based on web technologies. So the backend is a Pyramid web server. So this is a Python web server. We thought about using Node as well, but we decided in the end against it because we want to have a bit easier connection to the rest of the system, which is based mainly on ACS. And in addition, we have some databases that we want to connect to, and the Python is a very good solution for all of this. Now, the frontend itself is based on Polymer. Polymer is a library by Google. So if you have an Android phone or a Google account, then you're going to be very familiar with the design. It comes with lots of buttons, widgets, and stuff like that. But these are not really the main aspects of the GUI. The most of the logic is encapsulated inside the D3.js, which is a JavaScript library, which really comes up with, in my opinion, the most beautiful animations you can get for data-driven web applications. So all of this you will see in a moment. Just to talk a bit more about the backend. So some of the complexity that we had to sort of confront as we were developing this prototype is how to handle the huge amount of data and the diversity of the data that comes in from CTA operations. And part of the issue here is that you could have maybe two operators that sit in the control room, but you could also have, as a possible design feature, other engineers that are maybe off-site and they want to connect remotely, and they also want to view what's happening with the data. Even if they don't have active control, they would still be able to monitor, or maybe even a wider audience of users within the community, even though this is not a requirement at this stage. Additionally, we could have an engineer that's really on the ground. It's a big array, and maybe someone wants to go to one of the telescopes and check out what's going on the tablet, sees that they fix something, and it's okay. So in order to reduce the traffic and what happens when different users connect and try to connect to different data streams, then we decided to sort of buffer some of the data that comes into the system. And this little diagram here shows an example. So in this case, let's say we have two users and they want to access data from a couple of telescopes. So this is one of the large telescopes and one of the medium-sized telescopes. Details don't really matter, and maybe the monitoring database. So the monitoring database is another part of the system, but not necessarily all of the properties that you would be interested in are stored there. Because let's say you want to have your panel that features some parameter that is a sum or an average of two other parameters, right? So the GUI is not going to take charge of the system and start storing information. It starts the monitoring database, but it still has to somehow collect the information and update it. So we decided to use the Redis database as part of the infrastructure of the GUI itself. And then what happens is that you can create monitoring channels. Like for instance here, this could be an ACS monitor, or you could do polling or a notification channel. The information percolates upwards into the database on demand whenever at least one user requires this specific data point. It's stored there for a while, and then different users actually only connect to this Redis database, and they don't see what happens behind the system. So we factor out a lot of the complexity in this way, and this could help different panels to sort of work together without overloading the system too much. Now, if we want an example of one of the panels. So this guy will appear in a moment in a video, but just so that you're not too distracted by the animations, to give you a handle on what's going to go on. So this panel is an array monitor. It's a passive panel in the sense that you don't take any action with this, but you can explore what's happening inside the system. You start from here, from a global view. This is for the northern array, which is relatively small. It only has 20, 30 telescopes in the end. And these are deployed here in this pseudo-geographical layout on the ground. You have a mini-map here that gives you the same view, a quick list for the number of telescopes, and here you have some sort of global array parameters. And then one of the features that we've put in that we're going to have a zoom in this panel, and it's actually a semantic zoom, meaning that the type of animation, the type of graphics that you see is going to change as you change your zoom factor. So when you go inside, then instead of just a circle here, you get some more detail of what goes on within this specific telescope, and this panel also changes, and then you can further zoom in, and then you have additional information with this tree here that gives you all of the monitoring points for different pieces of hardware in separate subsystems that are in part of this specific telescope. And then let's watch the movie. Ignore for a second what happens here in this panel on the right, and we'll come to that in a moment. So what you see here on the left is that a user can zoom in on the panel, and then at some level it changes, you get some additional information, and then you can look at this tree here, and then this you can collapse the hierarchy if you want to look into further detail on what goes on in a specific subsystem. And everything, of course, is you can hover over it or you can click on it depending on the type of action you want. And one of the ideas is that this would be synchronized with a different panel that we're working on right now that would have, let's say, time series plots. So when you click on one of these circles here and you look at a specific data point, then you would get the behavior over time or histogram or something like that. And yeah, please, we'll get to this one in a moment. Now, another nice feature is that you have here this mini-map here on the top left that gives you a view of the context of where you are. So even if you zoomed in on this side, you still know where you are in the array. And if some red spot pops out somewhere else that you want to navigate to, then you can quickly click on that, or you can choose it from the list here. Now, the interaction between the two panels here is an example of panel synchronization. So the idea is that when you have some sort of problem and you want to investigate it further, then the information can come from different panels or different views of the system. So what you want is to be able to, let's say, click on a specific telescope, and then you want different panels that show you completely different aspects of the system to also go specifically to that telescope so you can easily see and investigate where the problem comes from. So in this case, it's pretty trivial because you just click on a specific telescope here, and then it also navigates to the same telescope here, but you can have more complicated reactions. The idea for the panel here on the right, just to illustrate, is that here you have a sky map. So this is the position where telescopes are pointing at. So you could look at the entire sky, but of course the way that we're going to do observations is that we're going to take a group of telescopes that all look at a specific point, a specific source in the sky, and then they work together. So you want to see that after you told the telescopes to shift somewhere, they're actually moving. So you can see this on the sky map here, where here on the right you have these encapsulated circles that correspond to subarrays, which is what I mentioned earlier, where you could say that some of your telescope would do some tasks and another group would do another task. So the groups here are divided by the types of the circle packing diagram, and then you can see which group of telescopes does what, are they all moving as they should. If the motor indicates some red alarm here, then you would also see it here as non-movement or something like that. Yeah, and maybe that's enough for now. So thank you very much.
Hi, thanks for the presentation, very interesting. So how is this implemented? Do you have a tree that tells you how these are mapped, or is it hard-coded? How configurable it is?
So nothing is hard-coded. This structure here, if this is what you're referring to, it accepts just a JSON object. So it's a nested dictionary. And then it builds the hierarchy by itself. It's a tree map. It's one of the bonuses of using D3. It has a lot of sort of built-in functionality that can help you do these kind of things and control how elements morph and how to do the animations and all of this. And it's all very dynamic, which is an important feature because different telescopes have different subsystems and different hardware, and you want to control all of that without tailoring the GUI. Even the deployment of the circles in this, or the way that things here are rearranged, this is all completely data-driven. So it means that each time you have some change in the way that the system behaves, all you need to do is send the new data, and it updates everything, and it knows how to interpolate the movements and everything, and it's all done automatically.
Thank you.
And by the way, yes, so this was mentioned earlier and I forgot to sort of address it. And in the first talk, there was a question about mobile devices. So this is probably too detailed to see on your cell phone, but it works perfectly well on a tablet. So if an engineer wants to take a panel like this or something different, then it's all well.
Okay, very nice. I think we have to wrap up now because there's the industrial talk. So thanks again.
Yeah.
Interesting.